Okay, so this week we're going to go into Unit 4, Predictive Maintenance. So predictive maintenance, we write it PDM, okay, and industrial and manufacturing organizations or companies, they usually try to implement PDM, okay, technology into their operations um, in order to get world-class status. Okay, so right now in North America, we've got only this much of percentage compared to the world class. So that's we're looking at the type of industry in assembly, distribution, manufacturing, small and large, process, consultants, opinion, and weighted average. Predictive maintenance, PDM. So what we do here is first we use the technology and analytical tools, and then we measure and monitor various systems and components, and then we compare the data with standards and specifications, and after that we predict or forecast the system or component failures. Okay, so in that way, if we can be able to predict the failures, we can be able to prevent them. Predictive maintenance evaluates the existing equipment condition and predict the failures, and then take appropriate steps to protect the system and components. So here in this example, you can see they're installing the sensors on the required equipment, and then they stream the real-time data directly into the system, and then they predict the machine failure. Okay, that's what we're doing here in predictive maintenance, and then alerts were put for the future maintenance requirements. Okay, and then you're going to schedule the maintenance task for that. So predictive maintenance totally rely on science, engineering, and technology, and we use that, okay, heavily use it to determine the current conditions, and then we predict the future conditions of any equipment. So for decision, we look at the critical equipment, and we look at the equipment criticality based on safety. Okay, remember the criticality. And then we also take a look at the production losses, and then we take a look at the cost of the equipment itself. Cost is a more serious consideration compared to all others. So that's what we look at every time we have to make a decision. Okay. PDM planning and implementation, again, we look at the cost benefit analysis, and then we have to come up with a very clear statement of objectives. And we always have to have ROI. Okay, that's a return on investments. Without that, it's pretty difficult to come up with costs to make decision on PDM. Predictive maintenance is totally quantitative in nature, because we always want to make sure that we know how, when, where, and by whom the data are collected. And also the measurement instrument can cause error, so we always monitor the instruments because they can also lead to faulty conclusions. And this is the reason why it is quantitative in nature. We look at the purpose for any data collection, and the whole thing, okay, for PDM is very time consuming and also costly. That's why we always take a look at the cost-benefit analysis. Data collection. So we have two methods. The first one is fixed and the other one is portable. So in fixed data collection, we use the remote collection systems, okay, especially for the harsh environment where you can't go, okay, access to that point. We call them access points. If you can't do that, we do the remote collection systems. Automated data collections are nothing but your recording system, directly recording the machine, okay, or the line. And we use the radio frequency devices, sensors, various microprocessors. And by using them, we reduce the human errors. The portable type, the second one, you usually is a portable devices like your cell phone, your iPads, okay, and handheld devices. And you can take it from one piece of equipment to another, so they're very good, okay, very convenient to use. So that's two data collection methods, fixed and portable. Data analysis. So we do chemical engineering, or we do again heavy stat, or a combination of them, okay, to analyze the data. And then we compare the outcome from the data with the standard. Standards, we call them baselines. All right, if you hear the common word baseline, we're talking about the standard. And after that, we analyze the data, we study the trends, what's going on with the data that you have collected, in order for us to come up with a conclusion. So the data that we use are past or historical data, we call them current. And then we're going to project that data to predict the future trends. Okay? You're going to have like two trends, so that's how we compare the past data and then project it to get the future data or trend. So finally, we determine the equipment status. Even if we say equipment, this can also be a big system, okay, all the components. And then we make the decision on a course of action. Okay, now we're going to get into the techniques. The very first one, we analyze the vibration. We call that vibration analysis of the system or components. So most operating equipment system, again, or components, they have some level of vibration. We're all subjected to vibration, even if you don't know, because almost everything in the world and in the universe are in motion, or even if they are taking a place, okay, in the space, so that's your potential energy, even that you still have the vibration. Okay? So vibration early warning sign, okay, we call the vibration the early warning sign because your equipment is deteriorating. Okay, so the level of vibration is so important for us to be able to understand the equipment level of deterioration. So we gotta always monitor the vibration. So the common causes of vibrations are imbalance of a rotating part, misalignment, defective bearings, and defective belts. Okay, so they're all in motion. And vibration monitoring. So we try to detect the vibrations, and then we judge the vibration, okay, what level that equipment is in for the vibrations, and then we're going to prevent the equipment failure. Depends on that level. So the factors affecting the vibration levels are size, stiffness, weight of the equipment, rigidity of the base on which it is mounted. So here you can see, and the surrounding equipment. Okay. So those are the factors that we're looking at in order for us to be able to decide the vibration levels. So here you can see the tech is completely studying, okay, taking data of the vibration of this machine. Okay, so when we monitor the vibrations, we take a look at the pump, compressor, reciprocating equipment, so on and so. And these guys, they have higher level of acceptable vibration. And those guys, the rotating equipment, okay, they have lower levels of acceptable vibrations. So here, these are examples of the rotating machine or equipment, and these are the example for your pump, compressor, and the reciprocating equipment. Standards. We follow ISO, okay, International Standard 2372. So here, that's your velocity, range, limits, and machinery classes. Then we take a look at the vibration severity. Okay, here you have example 4, okay, equipment right there, and classification A, B, C, and D for this example. So that's various levels of vibration severity. We're looking at them and the extent to which the vibration level is acceptable for a given class of equipment. Okay, so here A is good category, B kind of satisfactory, C is unsatisfactory because when you look at the level, it's going up, and D is completely unacceptable. Here you can see it's only 1.0. Okay, so that's your vibration severity. So also put them in a different class: class 1, class 2, class 3, and class 4. Class 1, we call them a smaller machine. Class 2, medium-sized machine. Class 3 is your rigid support. Okay, rigid support means like that. The foundation is completely rigid and really heavy. And if this is not that heavy, we call that flexible support. So that's how we classify, okay, the system, equipment, or components. Alright, here in this table, you can get the effects of vibration on equipment condition. So here is your vibration velocity, and we use RPS per unit. Here is the equipment condition. When you take a look at this column, it's going up, okay? So right here at 0.15 IPS, vibration velocity, the equipment condition is usually low force level, bearing life is 10 to 16 years minimum, with proper lubrication. When we go up there on 0.90 IPS, extremely high forces, bearing is damaged with every revolution. Bearing life ranges from 3 days, really short, to a few weeks. Okay? So those are the effects of vibration that can do on your equipment condition. So you definitely need to monitor this velocity in order to decide the vibration levels. Vibration monitoring equipment, we use many different kinds. We have portable or built-in monitoring devices, and then we collect and then we graph the data. Okay, so these are the data points that we get from your monitoring device, and we will develop this graph. We call it vibration signature. Okay, and here is your engineering limit, meaning you can go over that for this equipment. So here when you look at it, 0 going all the way to 0.9, beyond that, that vibration velocity is really, okay, not acceptable. It's bad, very dangerous, bad. So that's the inches per second, IPS. And here are your data points coming out from your monitoring devices, and you plot it. And when you take a look at it, from here to here is okay, from here to here is satisfactory, and from here to here is kind of warning, not acceptable, and from here to here is a danger zone of vibration. Okay, so it depends on these zones, we're going to take care of the equipment. Alright, so monitoring device, the first one is your vibration transducer. they look like that because there are many of them in the market. Okay, you can easily buy them. So there are three different types of transducer. One is acceleration, another one is a displacement, and the last one is your velocity. So here when you take a look at the transducer in two-dimensional, okay, drawing, you're going to see the sensitivity is right here, okay, that completely detecting the vibration along the axis. Okay, so along that axis, along this exit, along that exit, and along this exit. Okay, so those are three different types of your transducer. They are doing nothing but monitoring the vibration. Okay, here is a handheld, a very small fault detection instrument. Okay, this one is your lightweight vibration monitoring devices. We call them SKF vibration pens. These are the CMBP models. Okay, many companies like them, use them because it's really easy to use and also portable. Vibration charts, they look like that. We're not expecting you to draw any of it. We only expect you to know what they look like. Okay, there are two types: time waveforms and spectrum. So that's for your vibration charts. The time wave forms looks like that, and they're in a sine function. A sine function usually give you the wave, and we call that, if you remember your physics from high school, we call that a simple harmonic oscillation. Okay, here is one oscillation, 2, 3, so and so. So we're doing nothing but plotting the distance or displacement, and we're looking at as a function of time. Okay, so as time goes by, we are monitoring the activity, which is your vibration, and plot it, and you can see the very first one is your time waveforms, like this, vibration, okay, going in a period of time. Okay, now here, when you apply the force, so here is your force 1 and here is your force 2. This is your combined. So you can see force 1 at 5, okay? So that's how you look at it. And force 2 is between 0 and 5. So you can see dub, and then dub, and then dub, and then dub, okay? The same as your heart, okay? Vibration in the hospital, you can see that your heartbeat is going this type of sine wave, okay? The dub and then dub, two dubs. So kind of like that, vibration is similar to your heart rhythm, okay? But the machine vibration, they have a different waveforms, okay? This is just an example. Some of them are very complicated, so you might have like 4 or 5 peaks at the same time. Okay, so here is an example of a time waveform. See, so many peaks, so therefore you have so many forces on that part, component, system, or equipment. Okay, so that's what you normally see when you analyze your vibration coming out from these devices. You only have to know what it looks like, right? Alright, the next one is the spectrum. So for spectrum, you're going to see a different graph. Okay, pay attention. Definitely many forces here, forces acting on a part, a system, or an equipment. So if you can be able to recognize the differences in spectrum and the time waveform, I'll be very happy. Okay, so that's it for the first part of Unit 4, and we're going to continue on Thursday for Part 2.